Hello students, welcome to your first presentation for electromagnetism. Although it looks like we've got a fair bit of stuff to cover in this presentation, a lot of it you've probably already come across it before in year 11. The main thing that we're going to be looking at is effectively an example of each of these equations which are in your syllabus. Depending on what you covered when you're in year 11, you might have already seen all of these equations before, maybe just phrased a little bit differently. So the one thing I just want to make sure we understand before we continue is the concept of charge. So you know that we have a positive charge and a negative charge in the universe. So the electrons of an atom, they are negatively charged, and the protons of an atom, they are positively charged. And something that I'm sure you also already know is that if you have two charges next to each other that are the same, then they will repel each other. And if you have two charges that are opposite each other, they will attract each other. Something that you may or may not know is that we have an SI unit for charge, and we call that Coulomb. And since charge comes from sort of, for example, the electron, we can get to a point where we only have one electron, and that will be considered the smallest amount of charge that we can have. So that amount of charge in coulombs is 1.6 times 10 to the negative 19 coulombs. So you should never be able to get an amount of charge that is something smaller than that. So speaking of coulombs, we're going to look at this idea of Coulombs Law. Now this in previous years was actually in the year 11 curriculum, and if you've been in my year 11 class, you know that we cover that anyway because it flows on quite nicely. But if you haven't seen this before, it looks pretty complicated, but it isn't. Essentially, what Coulomb's law tells us is that there is an electric force that exists between two charged particles, which you already knew, except now, thanks to Coulomb's law, we're going to be able to quantify that and talk about how much force there is between two charges based on their separation and the amount of charge there. So if we were to break this down into its little components, the first thing that comes out immediately is that you're measuring the force, or you're calculating the force in newtons, and then this massive equation here, this massive part of the equation here, 1 divided by 4 pi epsilon naught, which is the permittivity of free space, or I think in your data sheet it's called just the electric constant. This number is a constant, the whole thing is a constant, and you can actually just say it's 8.99 times 10 to the 9 if you like, if you want to put it in your calculations like that, or you can resolve it when you're working your stuff out. With that constant, you multiply that by the product of the two charges involved. So you'll have two charges that are either repelling or attracting each other, and you need to figure those out and multiply them together. And then once you've got the product of the charges combined, you are going to divide it by the distance between the two charges. So if I have a positive particle there and I have another positive particle there, that R value is the distance between those two particles. So knowing that, you should now be able to answer a nice and easy question. If we have two electrons that are placed 6 nanometers away from one another, what is the force between them, and what direction is the force acting in? You might be a little bit confused by the use of nanometers. So nanometers is times 10 to the negative 9. So that distance there is 6 times 10 to the negative 9 meters. Okay, give that a go, press pause, and I'll see you on the other side. Okay, so hopefully you had a decent crack at that. So the first thing you want to write down is, the formula you're going to be using. So 1 on 4 pi epsilon naught Q1 Q2 over R squared. So once you've gotten to this point, you have to figure out what you know and what you don't know. So the first thing is that this particular part here is a constant, so you've got nothing to worry about. It's these things here that you need to sort of resolve. Now, the question's saying that you have two electrons that are placed 6 nanometers away, so the distance has already been figured out, and now you just have the charges. And since it's 2 electrons, Q1 is going to be equal to the charge of an electron, and Q2 is going to be equal to the charge of an electron. So you can rewrite this as 1 over 4 pi epsilon naught, and you'd have E times E over r squared. So it's important that I just point something out here. Whenever we have questions like this in tests and exams, students often get this particular part wrong. Instead of writing e times e, which would resolve to e squared, they actually, what they do write is, I'll just erase this for you, is they'll write 2e, and that's wrong. So essentially what this actually should turn out to be is e squared. So if you put that through a bit further, you'd end up with 8.99 times 10 to the 9. So that's that constant that we're talking about. Again, you don't have to resolve it yet if you don't want to. 1.6 times 10 to the negative 19. I'm going to square that because it's e squared. And then I divide that by the distance squared. And again, another common mistake is not squaring that distance. And if you put that in your calculator, what you'll get is 6.39 times 10 to the negative 12, and it's a force, newtons. And the second part of the question is asking you what direction is that force acting in. Essentially, you would just write that as being a repel force because they're both electrons, they're like charges, and they repel. Okay, so taking a break from the calculations just for a second, I want to talk about electric field diagrams. We'll cover these in more detail as we progress through the unit. But electric field diagrams are drawn using a convention, and it's important that we know what that convention is. So for electric field diagrams, you draw your arrows going from positive to negative, like you can see in this diagram. So if I have a positive charge and then I have another positive charge, and I have a negative charge here, then what I need to do is make sure that I draw my charges, not the positive. You cannot draw lines going from positive to positive. I can draw these lines here starting off, and then I know that what's going to happen is these charges will continue to actually sort of, or the force lines or the lines will sort of diverge like that, and then something like so. Now I'm drawing this on a stylus, and there's something really important about drawing field lines that I'm not doing a very good job of demonstrating that for you, and that is that when you draw field lines for electric charges, it's important that when you draw an object, so I'm going to draw it over here, if you draw field lines coming into that object, it's important that those lines come out perpendicularly to the surface. So that's the sort of thing that you want to demonstrate. You don't want to show lines doing things like that where the field lines are coming out and they're not perpendicular, because I can tell you that a lot of exam marking keys and a lot of test marking keys, they will focus on whether or not you have made a perpendicular connection with the object that is charged. So just keep that in mind. So back to the calculations, let's give this a go. So you can see that I've got a charged plate on this side, and that plate is charged with positives, and then I have a negatively charged plate on this side with a gap in it. But you can see that the field lines are actually going in a straight line, they're coming out perpendicular, and they're moving from the left to the right. So they're going from positive to negative. So this diagram is following that convention. But what you notice is at the edge, it sort of shows that the field line is bulging out on the edges. Now, some diagrams will have that and some won't. To be quite honest with you, if it was something like this in a test, I've never seen it where you'll be penalized for doing one way or the other. But essentially, this bulge just illustrates that there is sort of free space on either side, and so the field line has the potential to sort of go around that boundary. So I'm going to use this diagram to illustrate the concept of electric field strength, and that can be given by this equation here, where E is the electric field strength, F is the force, and Q is the charge. And remember, quite often the charge of Q, if it's an electron, Q is just going to be E, or if it's a proton, Q is just going to be positive E. And the good thing about this diagram is it demonstrates what an electric field diagram does is it actually shows you the direction that, or the direction of force that a positive charge will experience in that field. So you can see in this diagram, this charge here, this positive Q, is going to experience a charge towards the right, and that follows the convention that you've field diagram because the arrows are going to the right. Now, if that was a negatively charged electron, for example, well, you know that negatively charged, so I'm going to draw it in there to sort of illustrate it. So if I have a negatively charged electron here, you know that it's going to experience a force in the opposite direction because it wants to say hello to the positive charge over there, and it's repelled by the negative charge over here. So the field diagrams, another way to sort of help you remember how to draw them, is the field diagram should show the direction of force experienced by a positive charge in that field. And just a quick point before we move on, I want to illustrate where we have the electric field strength formula here. Just to clarify that this E is not energy, it's the electric field strength, and it can be thought of similar to the gravitational field strength that we've talked about before, where the gravitational field strength is the force per unit mass. So much the same way as the electric field will affect a charge, the gravitational field will affect a mass. So when you look at these problems, you'll find that there's lots of similarities into how you approach them and how you work with them. Another example of this, if I can go back to the previous slide of Coulombs law, is you notice that the force on a charged particle is equal to a constant multiplied by each of the charges divided by the radius. And if you've been pretty clever about it, you would have noticed that the gravitational field the gravitational force is equal to a constant multiplied by the two masses, okay, divided by r squared. So the formula for the gravitational force is written in the same way as you'd talk about the electric force. Anyway, moving on. Let's have a crack at this question. So a battery is connected across a piece of copper wire which results in an electric field of 3 newtons per coulomb created in the wire. What is the force on an electron within this wire? So if I was to draw the diagram of that, you've got this battery and you're just connecting it across a wire. Now what happens is an electric field will get set up across that wire. So here's your positive end, there's a negative end. So you would have a field that sort of moves from positive to negative, and therefore the electrons are going to be moving in this direction. So the electrons, I better make that very clear. The electrons will move clockwise, and therefore the positive charge, which is influenced by this field, will move anti-clockwise. But that's not what the question is really asking. The question is saying, what is the force on the electrons in this wire? So the formula you're going to be using is going to be that the electric field strength is equal to force divided by charge. Have a go at that. Okay, and to answer that question, it's just going to be E is equal to force divided by Q, and you've got the electric field strength. So you're just going to rearrange that equation to get F equals EQ. Remember, it's like almost the same as saying F equals MA. And you have 3 times the charge on of an electron, so 1.6 times 10 to the negative 19. And you should end up with 4.8 times 10 to the negative 19 newtons. And one of the questions is, well, should I have a negative there because the charge of an electron is negative? Sure. Okay, and the last equation we're going to be covering is one that involves potential difference. Now, you would have heard of potential difference in year 11. Another word for it is voltage. As you know, some people don't like using the word voltage. It's completely up to you. But effectively, the potential difference is the change in the electric potential that a charge has when it moves from point A, in this case, to point B, divided by the amount of charge. So this positive charge here has the potential to move from A to B because it is within an electric field that is going to be pushing it in this direction, which means it has a potential to move. And so we can say that the potential difference is going to be how much energy would be or can be transferred, how much work can be done, divided by the charge of that particle. This equation is often also given as work is equal to the potential difference multiplied by the size of the charge. So have a crack at this question. You have a 12-volt motorcycle battery that can move 5,000 coulombs of charge and a 12-volt car battery that can move 60,000 coulombs of charge. how much energy does each battery deliver? So you would just rearrange the equation, as I mentioned before, as work done or the energy transferred is going to be equal to the voltage multiplied by the charge. So for the first case, you would have the work times VQ, and that's going to be equal to 12 volts times you have not so much charge, or 5,000 coulombs of charge, and you'll end up with 60,000 joules. And if you did it the other way around, with the car battery, you'll end up with 12 volts times 60,000, and you'll have 720,000 joules. And I guess the point that this question sort of makes is that both batteries, a car battery and a bike battery, they both have the same voltage. They both have 12 volts. However, you have one battery that has a lot more charge in it than the other battery. And because it has more charge in it, and eventually it's going to deplete all of that charge, it can produce a lot more work, or it can use up a lot more energy, or it actually has a lot more energy within it, depending on how you want to look at it. Okay, so this is something that's more year 12-ish. We have an X-ray machine, and it works by accelerating an electron through a potential difference of 100 kilovolts before colliding with a target and then emitting X-rays. And we'll look at the collisions and emission of X-rays at another time. So the first part of this question is probably that you need to sort of understand what is going on. So if you have, say, so it's accelerating an electron, so you're probably looking at a negatively charged plate, and then you have a positively charged plate, and you have an electron sitting there, and that electron is going to be moving in this direction within a field. And if I was going to draw the field, I would say that the field is sort of doing this, because again the field lines go positive to negative, and I probably shouldn't be drawing dotted lines if I was honest with you. So this electron over here is going to be undergoing a change in energy as it moves towards this positively charged plate. What happens after that, you don't have to worry about. The point that it's saying is, what is the speed of this electron right before it hits this plate? So you know that it has a potential difference of 100 kilovolts, and you know its charge. So as it moves through here, it's going to be gaining energy. Once you know how much energy that is, can you then translate that to a velocity? So you have the energy gained is going to be equal to the work done on that electron. And that work done is going to be the potential difference that it moves through multiplied by the charge in that particle. So for this particular case, it's going to be 100 kilovolts, or 100,000 volts, times the charge on that electron. And you should end up with 1.6 times 10 to the negative 14. So this is how much energy this particle over here, how much energy that particle is going to have when it lands here. I just need to know that this energy is equal to half mv squared, which is equal to 1.6 times 10 to the negative 14. And then I can solve that by saying, okay, well, that means v is going to be the square root of 2 times 1.6 times 10 to the negative 14 divided by the mass of an electron, which is 9.11 times 10 to the negative 31, I think. And your answer will be 1.87 times 10 to the 8 meters per second. Now, about that answer, if you get a result where your answer is above 3 times 10 to the 8, so you've got something that's traveling faster than the speed of light, you've probably made a mistake, or the question is very, very bad. Just keep that in mind. Now, with a question like this, there's actually a shortcut or a faster way that you can work it, and you've probably already figured that out, because a lot of questions will ask you how fast is a charge particle going to be going given these bits of information. Well, if you have the energy or the work done on the charge, and that all goes to the kinetic energy on that particle, then you can rearrange that to get velocity as equal to the square root of 2 times the charge times the potential difference over m, keeping in mind that this v and this v, one is uppercase, one is lowercase. But that equation there can also be used. Okay, and that's it for this presentation. The point of this one was to make sure that you understand some of the basic concepts that we brought forward from year 11, and you also got to know a couple of new equations that you'll be using throughout this module. Once you've done that work, we should be good to continue on, and we'll start looking at magnetism. Thank you.